Good morning, everyone, and welcome to my lecture. I'm here today to lecture on the stability of slopes. Here we go. Failures of natural and man-made slopes have caused much death and destruction, economic losses, and environmental damage all over the world. Some failures are sudden and catastrophic, others are insidious. While some failures are widespread, others are localized. Question is, what types of slope failure are common in soils? Let us go through the most important types of slope failures in soils. In rotational slips, the shape of the failure surface in section, as shown in the figure here, may be a circular arc or a non-circular curve. Generally, circular slips are associated with homogeneous soil conditions and non-circular slips with non-homogeneous soil conditions. Translational slips tend to occur where the adjacent stratum is at a relatively shallow depth below the surface of the slope. In that case, the failure surface tends to be plane and roughly parallel to the slope, as you see in the figure here. Compound slips mostly take place where the neighboring stratum is at a greater depth. The failure surface in that case consists of curved and plane sections, as you see in the figure here. Finally, translational and compound slips, as the name suggests, it is the combination of translational and compound movements. They happen where the form of the failure surface is affected by the presence of a bordering stratum of significantly different strength. By the way, what factors trigger slope failures? Some of the main factors are as follows. Water and wind continuously erode natural and man-made slopes. The act of erosion changes the geometry of the slope as shown in the figure, ultimately bringing about slope failure. Streams, rivers on the other hand, frequently scour their banks, thus weakening their natural or man-made slopes as illustrated in the figure here. Long periods of rainfall saturate, soften, and even erode soils. Water enters into existing cracks as illustrated in the figure here and may weaken underlying soil layers, thus causing the failure of slope. Loads such as a building, a bridge pier, and etc., placed on top of the slope will increase the gravitational load and may induce slope failure. Earthquakes bring about dynamic forces as illustrated in the figure here. Vertical and horizontal dynamic forces acting through the centroid of the sliding mass. Particularly dynamic shear forces that reduce the shear strength and stiffness of the soil. In saturated sand, pore water pressures could increase to a value equal to the total stress and cause saturated sands to behave like viscous fluids, a phenomenon known as liquefaction. Consequently, lateral displacement of sloping ground happens as illustrated in figure 6. The dynamic forces are so quick that excess pore water pressure has no enough time to dissipate. Thus, failure takes place under undrained condition. Lots of slope failures are commonly due to unidentified geological features. A thin layer of silt, as illustrated in the figure, under a thick deposit of clay can easily be omitted during drilling operations, or one may be careless in evaluating borehole logs, only to find later that the existence of the silt caused a destructive failure. Sloping, layered soils are vulnerable to translational slide along weak layers. We can easily divide slope failures owing to construction activities into two cases. The first one is excavated slope, and the second one is fill slope. Excavation activities next to the toe of an existing slope may result in failure because lateral resistance is removed. Fill slopes, as you see in the figure, are popular in embankment construction. Soil is placed layer by layer at the site, and each layer is compacted according to related specifications. In any case, the soil is unsaturated and negative pore water pressures set up. The embankment is generally placed on a natural soil, which is called foundation soil. If the foundation soil is saturated, then the positive pore water pressures will be produced because of the weight of the fill and the compaction process. The effective stresses decrease, and as a result, the shear strength decreases too. With time, however, the positive pore water pressures dissipate, the effective stress increase, and so does the shear strength of the soil. Therefore, slope failures in fill slopes are most likely to happen during or immediately after construction. Reservoirs may be subjected to rapid drawdown. In this case, the lateral force provided by the water is lifted, and the excess pore pressure does not have sufficient time to dissipate. As a result, the slope can fail under undrained condition. If the water level in the reservoir stays at low levels and failure did not take place under undrained condition, seepage of groundwater would set up, and the additional seepage forces could bring about failure. Slope stability analysis is a procedure that geotechnical engineers use to evaluate the stability of natural and man-made slopes. It contains the use of factor of safety. The factor of safety is defined as the ratio between the available and required shear strengths along an assumed or a known failure surface. In here, the available shear strength is the maximum strength of soil mass as defined by the equation given here. And the required shear strength is the strength that is needed to keep the slope stable. When factor of safety is greater than unity, the slope is considered to be stable. However, if the factor of safety is less than unity, it is assumed that the slope fails. Now then, what if factor of safety equals unity? The slope is still considered stable. Nevertheless, we should be careful with factor of safety values and remember that it is only a number that may not precisely show the slope conditions. Slope stability analysis includes some assumptions and simplifications, which may be different from the existing stress or shoal conditions in the field. For this reason, there have been several cases in practice where slopes with factor of safety less than unity were still stable for a long period of time. Slope stability problem in general is considered two-dimensional, conditions of plane strain being assumed. It has been shown that a two-dimensional analysis provides a conservative result for a three-dimensional analysis. Some failures happen on slopes where heavily weathered rocks or soils are underlain by a hard layer. Such landslides are characterized by relatively shallow depths, about 1 to 2 meters, and produced by rainfall or earthquakes. The stability of such slopes can be analyzed employing the infinite slope method as illustrated in the figure. Now, consider that there is seepage through the upper layer of soil as shown in the figure, and that the groundwater level is at the ground surface and an element within the slope of weight W. Now, the pore pressure at any point within slope can be obtained by the construction of flow nets or inserting a standpipe at any point and measuring the groundwater level. Let the excess pore water pressure caused by the seepage be U at the base of the element. Other forces acting on the element are T as the tangential reaction force, N as the normal total reaction force, which are the components of the weight of rhombic element, sigma as the normal total stress, and tau is the tangential shear stress. X1 and X2 are shear forces acting on the both sides of the rhombic element as shown in the figure. And finally, E sub 1 and E sub 2 are normal forces. For a uniform slope of infinite extent, X sub 1 equals X sub 2 and E sub 1 equals E sub 2. Now then, the normal force can be expressed as the weight of rhombic element times cosine beta. Beta is the angle of slope. Therefore, the total stress can be defined as a ratio between the normal force divided by the cross-sectional area of the rhombic element. Accordingly, effective stress, which is the difference between the total stress and the pore water pressure, can be formulated as given here. In a similar manner, tangential force can be defined as the the weight of rhombic element times sine beta. So the tangential shear stress can be obtained dividing shear force by the cross-sectional area of the rhombic element. If we remember that the maximum shear strength of soil is equal to C prime plus sigma prime times tangent phi prime, then we can simply define the factor of safety as a ratio between the maximum shear strength and the shear stress mobilized along the failure surface. Now, if we include all the definitions made earlier into this equation, we can formulate factor of safety in the form given here, where U is the pore water pressure at point F shown in the figure earlier. If we rearrange pore water pressure and put it into the above equation, we formulate the factor of safety in the form presented here. With the help of factor of safety developed for stability of infinite slopes, 6 special cases can be considered. The first one is dry cohesionless slope. Well, in this case, the factor of safety will be reduced to the equation given here. So for critical case, which means when the factor of safety is equal to unity, then beta is equal to phi prime, which means that the angle of slope is equal to the internal friction of soil mass forming the slope. The second case is the wet cohesionless slope. The factor of safety in this case will be modified as shown here, where gamma prime is the effective unit weight and gamma bulk is the total unit weight of the soil mass forming the slope. Although there may be attractive force between particles due to surface tension regarding wet cohesionless slope, this is simply ignored to be on the safe side. The third case is the cohesionless slope with pore water pressure ratio. Now, instead of using pore pressure in the calculation of factor of safety, we use pore pressure ratio, which is defined as a ratio between pore water and the total stress. In this case, the factor of safety can be obtained by the equation given here. The fourth case is the cohesionless slope with water table below slip surface producing section. The capillary zone above the water table in a fine sand or silt can be important and will generate negative pore water pressure within this location. And the pore pressure in this location can be obtained by the unit weight of water times hs. Hs is the distance between the slip surface and the water table. The factor of safety in this case can be obtained using the equation given here. A simpler expression can be obtained if seepage through the section zone parallel to the surface is assumed. The pore water pressure and the factor of safety can be calculated using the equation presented here. But we must be very careful when assuming sections to act in support of a slope. The fifth case is the layered soil profile with groundwater level at the surface. With a layered soil profile, the tangential shear stress can be plotted with depth as shown in the figure here and compared with the available shearing resistance superimposed on it. And finally, the sixth condition is the undrained conditions. So far, the long-term condition is assumed to be critical using effective stress soil parameters. If the soil is under undrained condition, the factor of safety can be obtained by the equation given here, where Cu is the undrained shear strength. Let us consider a circular arc analysis under undrained condition. This is an analysis in terms of total stress and regards the short-term condition for a cutting or embankment, assuming that the soil profile is fully comprised of saturated clay. In this case, a section of the slope of unit thickness bounded by a circular arc is taken into consideration. Gravity forces tend to rotate the circular segment about its circle center, and this rotation is resisted by the shear strength mobilized along the slip surface as shown in the figure. Therefore, moment equilibrium is applied. The factor of safety against instability can then be defined as the ratio between shear resistance moment and the overturning moment. The shear resistance moment is equal to the force along the length LAB of the circular arc multiplied by the radius of the circle R as shown here, where theta is in radians. The overturning moment is equal to W times D. W is the total weight of the segment obtained from gamma times A, where gamma is the bulk unit weight of the soil and A is the area of the segment. D is the horizontal distance from the circle center to the centroid of the segment. The factor of safety is then formulated as presented here. The determination of the weight of the segment and D can require lengthy calculations. So it will be more convenient to split the segment into several slices as illustrated in the figure. The factor of safety is then provided by the equation given here. The area of each slice can be obtained from the mid-height multiplied by the width of the slide, and the angle alpha can be calculated. It is important to note that the sign of the overturning forces changes to the left and right of the circle center. What is more, the inter-slice forces are ignored. The question is the adopted slip circle the most critical one, which gives the lowest factor of safety? If not, what would be the method then? The center of the most critical circle can only be achieved by trial and error. Various slip circles are analyzed and the minimum factor of safety is obtained. A suitable procedure is provided in the following figure. The center of each trial circle is plotted and the F value for the circle is written alongside it. After several points have been established, it is possible to draw contours of F values, which are roughly elliptical, so that their center shows where the center of the critical circle will be. Note that the value of F is more sensitive to horizontal movements of the circle center than to vertical movements. This process can be time-consuming and tiring job, so the use of computer programs for heterogeneous slopes is highly advised. The slice method can also be used where the soil profile is made up of different layers and where there are other forces such as a surcharge at the top of the slope or a water-filled tension crack. As the condition of limiting equilibrium develops with the factor of safety close to unity, a tension crack as shown in the figure may develop near the top of the slope, through which no shear strength can be generated. And if the crack is filled with water, a horizontal hydrostatic force, as shown in the figure, will increase the disturbing moment by an amount of Pw times Yc. Yc is the distance as shown in the figure. The factor of safety will be further reduced because of the shorter length circular arc as shown in the figure, along which shearing resistance can be mobilized, and the upper part will be ignored because there will be no shearing resistance as stated before. The depth of a tension crack can be calculated by the expression given here, where C sub u is the undrained shear strength and gamma sub b is the bulk unit weight of soil. The hydrostatic force is obtained from the expression provided here. The expression for the factor of safety can then be rearranged in the form presented here. It is important to note that the width of the slices does not need to be the same for all slices. Stability analysis in terms of effective stress can only be conducted when there is a reasonably accurate assessment of pore water pressures within the slope. For a natural slope and a cutting, The more critical condition, which is the long-term condition, can be analyzed employing the effective stress analysis. The pore pressures can be represented by the steady seepage state when a flow net construction can be made, or when a non-equilibrium water table level is present. For an embankment, the short-term condition, which is the critical condition, can also be analyzed using an effective stress analysis, but these will be limited by the accuracy with which the excess pore pressures can be estimated. A circular arc slip surface is assumed with radius r. The soil segment above the circular arc is of unit thickness and divided into a number of vertical slices, generally of equal width and varying height, as shown in the following figure. In the figure on the left-hand side, you see the division of the sliding mass into several slices. And in the figure on the right-hand side, you see the forces acting on each slice. With a sufficiently large number of slices, the base of each slice can be assumed to be a straight line inclined at an angle alpha to the horizontal, as shown in the figure, and with a length which is equal to b times secant alpha. It is presumed that all of the slices rotate around the circle center as a whole body, so that the factor of safety is the same for each slice. In other words, there is one factor of safety for the trial slip surface adopted. This indicates that forces must act between these slices, known as inter-slice forces, and these are generally taken as normal and tangential to the sides of the slices. Now, the forces acting on a slice are the total weight of each slice, which is equal to bulk unit weight of soil times width and the height of slice. The weight of each slice will cause a shear force parallel to its base, which is equal to weight of slice times sine alpha. The total normal force on the base of a slice, which is equal to sigma times L. And finally, the shearing resistance of soil will result in a shear force which is equal to the shear stress mobilized along the slip surface times L. Total normal force can be obtained from the total normal stress, which has two components, namely the effective normal force, which is equal to sigma prime times L, and the water force, which is equal to pore pressure times L. The interslice forces can be represented as total normal forces, E sub 1 and E sub 2, and tangential shear forces, X sub 1 and X sub 2. Other forces on the segment, such as a foundation or any surcharge at the toe or crest of the slope, or a water-filled tension crack, ought to be included in the analysis. For moment equilibrium, the overturning moment produced by the shear forces must be balanced by the resisting moment of the mobilized shear strength forces as formulated here. With the earlier expressions involved into this equation, we modified as written here. Since the factor of safety is the same for all slices, it can be written as a ratio between the shear strength mobilized along the slip surface and the shear force. The shear strength of soil in terms of effective stress is equal to C prime plus sigma prime times tangent phi. And if it is multiplied by L, factor of safety can be written in the form given here. For a homogeneous slope where C prime and phi prime are constant along the slip surface, then the factor of safety can be rearranged in the form presented here, where LAB is the total arc length between points A and B. The solution of this expression needs assumptions to be made about the interslice forces, which influence the values of n-prime forces. In this regard, two methods are available. In Fellenius method, also known as the Swedish method, it is assumed that the interslice forces are equal and opposite and cancel each other out. It is now only required to resolve the forces acting normal to the base of each slice as illustrated here, where U is the pore water pressure, which is equal to unit weight of water times H sub W. H sub W is the height to the water table above the base of the slice, or related to the nearest equipotential if a flow mat is drawn. The factor of safety is then rearranged in the form as given here. Values of W, alpha, and U can be determined for each slice and presented in a table. The summations obtained by addition. It is important to state again a series of trial failure surfaces must be chosen in order to obtain the minimum factor of safety. This solution underestimates the factor of safety. The error, compared with more accurate methods of analysis, is generally within the range of 5 to 20% and would therefore be conservative. In Bishop's simplified method, it is presumed that the tangential interslice forces are equal and opposite, not the normal forces. Resolving forces in the vertical direction gives the expression presented here. Therefore, n prime can be expressed as shown here. Now, substituting for n prime into the equation gives the factor of safety. If the factor of safety is rearranged, we get the equation presented here. Since the value of factor of safety is available on both sides of the expression, a trial value for factor of safety must be chosen on the right-hand side to obtain a value of factor of safety on the left-hand side. By successive iteration, convergence on the true value of Fs, which is the factor of safety, is obtained. The factor of safety determined by this method is improbably to go beyond an error of 7%. It sounds that it is a time consuming and tiring job. Is there another way out? Well, the method is certainly better solved by using a computer program which can provide the factor of safety of a trial circle in a matter of seconds with respect to many minutes when carried out manually. This speed of calculation is also helpful in searching for the circle leading to the lowest factor of safety, where the computer programs will analyze circles over a grid of circle centers and with the circles passing through chosen points on the slope. The programs also permit more complex soil profiles, groundwater condition, external loading, and seismic effects. The pore pressure ratio can also be used to represent overall or local pore pressure conditions in a slope analysis. It is given by the ratio of pore water pressure to the total stress. The Bishop's equation can then be written accordingly as provided here, where non-homogeneous soil profiles are available, such as with layered strata, a non-circular slip surface may be more suitable. Employing the method of slices and regarding overall horizontal equilibrium as the stability criterion, the following expression for the average factor of safety along the slip surface is obtained. In this equation, MA is equal to the expression provided here, and dx is equal to x sub 1 minus x sub 2, which is the resultant vertical interslice force. A similar procedure for the solution of the Bishop simplified method is needed using an iterative procedure to converge towards the value of factor of safety and an assumption for the position of the interslice forces on each slice, and their magnitudes must be involved. When a cutting or embankment is constructed, the total stress in the ground are changed. This brings about a change in pore water pressure, and since the factor of safety of a slope decreases as the pore water pressure increases, the most critical condition will take place when pore water pressures are greatest. In the figure here, you see an embankment built on a fully saturated soil. For the construction of this embankment, the increase in total stress, as shown in the figure here, will lead to increase in pore water pressure considering a point A in the foundation soil. If the construction is carried out rapidly, the pore pressure increase will be greatest at the end of construction. And at this stage, the soil will be under undrained condition. The lowest factor of safety will be associated with these short-term condition, as you see in the figure here. But with time, as the pore pressure dissipates, as you see in the figure, then the factor of safety will increase accordingly. Therefore, most embankment failures take place at or near the end of construction. Now let us consider another case for cutting. The reduction in total stress during excavation will bring about a decrease in pore pressure at point A as illustrated in the figure depending on the soil type. If the excavation is carried out quickly, then there will be no sufficient time for redistribution of pore pressures. The pore pressure reduction will be greatest at the end of construction stage. For a cutting, the lowest factor of safety is associated with the long-term condition depending on the permeability of soil mass. If it is sand, the process will be quicker, but if it is intact clay, it may take several years. For an earthworm, the pore water pressures will change based on the level of the water confined in the reservoir as shown in the figure. So the following conditions should be checked. The first condition is when the reservoir is full of water. In other words, when the steady seepage condition is set up. And the second condition is when the water level, the confined water level, drops suddenly. Notice that figure shows pore pressure increases at point A on both sides. And the second figure shows the corresponding factor of safety. As the pore pressure increases, the factor of safety decreases. The lowest factor of safety obtained when the water level in the reservoir drops suddenly from level 1 to level 2. It appears that it is not an easy task to adopt an acceptable factor of safety owing to the multitude of factors which must be taken into consideration. What are then the usual ranges of factor of safety? A factor of safety between 1.3 and 1.4 ought to be used in design for first-time slides, and a factor of safety of about 1.2 for slides having pre-existing slip surfaces. Similar considerations should be applied to embankments as well. For earthworms, with similar considerations as mentioned above, factors of safety greater than 1.3, 1.5, and 1.2 could be acceptable at the end of construction after the steady seepage condition is established and after the rapid drawdown. In general, a higher factor of safety would be adopted where there is a risk to life and adjacent structures. By the way, is there any way to increase the stability of slopes if the factor of safety does not meet those criteria? Yes, there are several techniques. As you would appreciate, that is not possible to explain all of them in here. However, I will explain some of well-known methods briefly. The first one is the drainage technique. In this technique, we drain water away from the soil mass to increase the effective stress, thus increasing the shear strength of soil mass. Unloading is another technique. In this technique, we try to reduce some weight of sliding mass so that the driving forces are reduced. Reinforcement is used to fix the sliding soil mass back to the stable ground through anchoring, soil nailing, and or rock balls, whichever suitable. Grouting is used to provide adhesion between the sliding mass and the stable ground along the slip surface. And finally, retaining technique is used to provide support to the sliding mass of soil through retaining structures. Here you have a practical example. A cut for a highway is shown in the figure here. The cut is carried out in a medium clay which has the following properties given here. For the slip surface, as shown in the figure, which is a circular arc, determine the factor of safety using the Bishop simplified method for the long-term condition when the groundwater table at 5 meters below the crest level. Crest is the top level of the slope. The first step is to divide the cross-section into several vertical slices. In this example, the cross-section is divided into 12 vertical slices, and the values of alpha, the width, and the mid height of each slice are respectively determined. The weight of each slice is equal to bulk unit weight of soil times the width and the height of slices. The pore pressure is figured out at the midpoint of each slice as the height above the base of slice to the water table as mentioned before. And pore pressure is equal to gamma water times H sub W, where gamma water is equal to 9.81 kilonewton per cubic meter. A table is prepared for each slice showing the values of B, H, W, alpha, W times sine alpha, U, A and B, and A times B. A and B represents the expression given below the table here. Having defined the values for each slice, the related columns are summed and the total values are written below them as shown to calculate the factor of safety. Since the factor of safety is available on both sides of the equation, a trial value of 1 has been assumed for the expression on the right-hand side, leading to a calculated value of 1.31 with a revised value of 1.40, a calculated value of 1.394 is obtained as illustrated here. This is a hand calculation to obtain the factor of safety for the circular arc given in the figure. And this circle does not give the loss factor of safety. Therefore, it is not the critical slip circle. It will be appreciated that a hand calculation to seek for the critical slip circle can cause much trial and error, and the benefits of using a computer program are unavoidable. Employing a commercial software program, the slope given in the example above can be analyzed using a grid of at least 25 circle centers and a number of points beyond the toe for the circles to pass through. The contours of equal factor of safety plotted on the grid of centers gives a series of elliptical loops, which result in the critical circle center, thus giving the lowest factor of safety. Let me quiz you about what we have learned so far. The first question, in slope stability analysis, the factor of safety is defined as which option? Yes, it is A. The answer is A. Available strength divided by required strength. Jolly good. The second question, when factor of safety is equal to 1.5, it means that, which one? No, no, it is not. The answer is B. 67% strength mobilization. And the third question, the Bishop's simplified slope stability analysis is based on what? Yes, the limit equilibrium method. Well done. The fourth question is geological features and environmental conditions are responsible for most slope failures. True or false? Yes, it is true. So the answer is A. Nice going. The fifth question, the critical depth is the depth of tension cracks, which is equal to 4 times S sub U divided by gamma. True or false? Yes, it is false. It is equal to 2 times S sub U divided by gamma. So it's a little bit tricky here. And the sixth question, in fine-grained soils for short-term loading, only effective stress analysis is required. True or false? No, it is false. So the answer is A. Seventh question, the appropriate value of phi prime for fissured over consolidated fine-grained soils to use is phi prime sub r. True or false? Yes, it is false. Very good. The eighth question. Jumbo assumed a non-circular failure surface and considered equilibrium of horizontal forces. True or false? Yes, it is true. So the answer is A. Good job. The ninth question. For slopes in coarse-grained soils, only an effective stress analysis is necessary for short-term and long-term loading. True or false? Now, it is false, so the answer is A. The 10th question, tension cracks in fine-grained soils reduce the factor of safety of a slope. True or false? Yes, it is true. Very good. The answer as B. And the final question for slopes. Adjacent to the bodies of water, the effects of operating and environmental conditions on their stability should be considered. True or false? It is true. Congratulations. So the answer is A. That's it. Well, that completes my lecture. Thank you for listening. Hope to see you soon. All the best.